Our group was in charge of the first part of the reaction, so 14 plus 20 going to 16. We went through and identified the reagents and then came up with a mechanism consisting of 4 steps. On the left-hand side, you can see how we broke down the mechanism into 4 steps: protection, exchange, Grignard, and deprotection. On the right side, the reagents and conditions of the reaction are displayed. In the next few slides, we will walk you through these steps of the mechanism in greater detail.
This is a table of the reactants used in this synthesis. They are listed in order of their addition in the reaction, along with important values in each substance's reactivity role. The trimethyl silyl-chloride is used to create the protecting group on the amine through silylation. The first Grignard reagent, phenylmagnesium chloride, acts as a base to pull protons. The Grignard reagent lithium chloride complex is used as the reaction nucleophile. THF is the solvent in which this reaction occurs in. Now we will go through the reaction mechanism step by step. The scheme has been provided here as a reminder. The first step of this synthesis is the formation of protecting groups. We're working with Grignard reagents, which are very basic. In our starting material, we have 2 acidic protons in the amine group. If we add Grignard reagents without protecting these groups, there will just be an acid-base reaction. For this reason, we will protect the amine group using TMSCl, or trimethyl silyl chloride. We will be using a Grignard reagent to pull the acidic protons off of the nitrogen and then adding the TMSCl, which is shown in the mechanism. The protons are pulled off using a Grignard reagent, probably to prevent the presence of extraneous salts in the solution. There will already be magnesium salts present later in the solution, so adding some now from a Grignard will not make much of a difference. Once the amine group is protected, halogen exchange can occur.
The second step of the reaction is a magnesium halide exchange. The magnesium halide exchange method is a fairly new chemical pathway patented by Dr. Paul Nochel and Dr. Arkady Krasovsky. The Granger created in this method is highly active due to the coordinated lithium chloride salt. It is referred to as a turbo-Grignard. The isopropyl magnesium chloride lithium chloride complex is able to add itself onto the iodine through single electron radical movement. The remaining salt is able to coordinate to the iodine, allowing for isopropyl iodine to leave and the turbo-Grignard to be created. Following the creation of the turbo-Grignard, the next Grignard addition step may proceed.
So this is the Grignard reaction portion of the mechanism, and it's not too different from any of the Grignard reactions we've seen in class so far. So firstly, we're using THF as the solvent, which is important because it's an aprotic solvent, so the very basic Grignard reagent can't deprotonate the solvent. And as you can see in the mechanism, the sigma bonding electrons between the carbon and the magnesium attack at the carbonyl. And this is the major difference between this particular Grignard reaction and the ones we've seen so far. Only one equivalent of the Grignard reagent adds instead of 2 equivalents. And this leads to the formation of a hemiketal functional group.
In the deprotection step of the mechanism, the molecule is treated with an acid workup. The purpose of this addition is to remove the protecting groups that were added earlier in the mechanism. This is because, in order to achieve the desired product, no more Grignard reagents need to be introduced. Mechanistically, this step occurs by the nitrogen donating its lone pair to remove a hydrogen from the hydronium, while simultaneously the oxygen is donating its lone pair to remove the protecting group. This step repeats itself to remove the other protecting group. This step is important because it reactivates the amine, allowing it to be utilized further on in the mechanism if necessary.
In conclusion, this step of the mechanism creates a carbon-carbon bond between the 2 starting material molecules and leads to the formation of a hydroxyl functional group. This is important because in the very next step in the mechanism, this hydroxyl functional group is substituted with a nitrile group. Ultimately, this whole molecule serves as a leaving group in the final product and doesn't show up in the final product. It's important that this step is carried out through the second generation because in the initial generation, N-butyl lithium is used for the lithium halogen exchange. N-butyl lithium is highly reactive and actually catches on fire when it's exposed to air. So using these different reagents makes the reaction much safer, and it can be carried out on a much larger scale for reproducibility, and it also has much higher yields.